Welcome again to the video lecture series for GG and OCN312. In this video, we'll continue our discussion for solving higher order ODEs, that is the homogeneous case. And in this video in particular, we're going to look at the situation in which the coefficients are not constant. The coefficients on y and its derivatives vary as a function of x. And for that type of situation, we're going to focus on the relatively simple case in which the coefficients vary according to the Cauchy-Euler equation. It's a special form that has a relatively simple solution, so that's what we'll focus on. After going through a derivation of the solutions, I'm going to show you that there'll be three situations in which you will encounter. The first being when all the roots of the second order equation are real. The second being when the roots are repeated. And then finally, the case in which the roots are imaginary. And we'll go through some examples to illustrate those cases and how to solve them. So your aim in watching this video and in doing your homework, your main goal will be to develop your ability to both recognize the equation of the Cauchy-Euler form and then find the general solution to the second order ODE in that form. In fact, you'll have some knowledge on how to solve higher order cases, but we're really going to focus on the second order case. So again, this comes from Greenberg 3.6. And this is the homogeneous case with non-constant coefficients. And I'll just remind you of the general form of the general ordinary differential equation. So we have the nth derivative of y plus a coefficient, which we called p1, generally is a function of x, times the n minus first derivative. And we're going to add subsequent terms with reduced derivatives all the way down to the Pn minus 1 coefficient times y prime, the first derivative, plus the last term being Pn of x times y to the zeroth, just y. It's the zeroth derivative, or just y. And that it's homogeneous, so it's equal to 0. And so before, we solved the case when the p's were constant. The coefficients, those are the p's, were constant. So now there'll be many situations that you might encounter in which the p's vary as a function of the independent variable x. So I guess in section 3.6.1, the special form of that sort of equation is the Cauchy-Euler equation. Again, it's a special form of p of x, and that is x is raised to a power that is the same order of the differentiation on y. So this would be, right, so we have y to the nth power times x to the n plus some constant times x to the n minus 1 power times y to the n minus first derivative. Again, these quotation marks distinguish, or sorry, the parentheses distinguish derivatives from just raising a number to the n power. And that's summed all the way down to the Cn minus 1, which is a constant, times x to the first power times y prime plus Cn times y. Okay, so again, the power on x is the same as the order of the derivative on y, and that's a special case in which the coefficients, the p's, are not constant. So the most common situation in physics, for example, is the second order Cauchy-Euler case. So that's x squared y double prime plus our constant times x y prime plus c2 times y is equal to 0. So let's consider how to solve this. Now before, when the coefficients were constants, we found solutions of the form e to the lambda x. So we might imagine that this has a similar form, but if we try this, we get a characteristic equation that's a function of x. Remember, the characteristic equation was by assuming that y was proportional to e to the lambda x and substituting that into the equation, and we find, and from that we get the characteristic equation. And in this case, the characteristic equation is x squared lambda squared plus c1x lambda. Remember, the power on lambda has turned out to be the same as the order of the derivatives when we use the equation of this form, plus c2 is equal to 0. Now, the problem with this equation is, remember, we assumed that lambda was constant, right? But in order for this equation to be true, lambda must be a function of x. So in order to satisfy this characteristic equation, lambda would have to vary as a function of x, and that violates our assumption that lambda is constant. So this is not the right solution. So this is right. So again, this doesn't work, and it doesn't work for this reason. So we have to seek an equation of another form for the solution. So what about trying y is equal to x to the lambda? Let's try this. And again, our initial equation is x squared y double prime plus x times c1 times y prime plus c2 y is equal to 0. So y prime is equal to lambda times x to the minus lambda, and x times y prime is equal to lambda. I'm sorry, y prime is equal to, I didn't do that right. Lambda is equal to lambda x to the lambda minus 1. And so the product of x times lambda prime is lambda times x to the lambda. And now the next term we need to evaluate is x squared times y double prime, and that's equal to x squared times the derivative of this. And so x squared y double prime is equal to lambda times lambda minus 1 times x times lambda minus 1 times x squared. I'm sorry, this is x raised to the lambda minus 2 power, because we have to subtract 1 when we take the derivative of lambda minus 1. And then that's all multiplied by x squared, as we've done here. And it turns out that this is equal to lambda times lambda minus 1 times x to the lambda. So with the Cauchy-Euler equation, again, when we're multiplying the functions of y, the derivatives of y, by the power x raised to the same power as the order of the derivative, what we get is the first term, well, both terms being proportional to x to the lambda. And so this gives lambda times lambda minus 1 plus c1 times lambda plus c2, and that's all multiplied by x to the lambda, and that's equal to 0. So we get a new characteristic equation for lambda. And since that equation is all in terms of constants, that is consistent with an assumption that lambda is constant. And that characteristic equation is lambda times lambda minus 1 plus c1 lambda plus c2. So that gives us this is a new equation that we can use to solve for lambda. And so if we were to put this in terms of the form of a quadratic equation, we would get lambda squared minus 1 minus c1 times lambda plus c2 is equal to 0. So we have a quadratic equation, and so we will have, we can solve that using the quadratic formula, where lambda is equal to negative b, which is 1 minus c1, plus and minus the square root of b squared minus c1 squared minus 4a, which is 1 times c2, all over 2a, which is just 2. A is 1 here. So this will allow us to get to the solution of the form y equals x to the lambda, which appears to work. Now, one thing I'd like you to notice is the nature of the solution depends on the sign of what's under the square root. And let's call this term right here delta. So delta is equal to 1 minus c1 squared minus 4c2. So you should be able to see that if delta is positive, then the square root of a positive number is a real number, and lambda has two distinct real roots. So that's the first type of solution you'll find. That is when what's in the square root is greater than 0. It's positive. Now the second situation occurs when when what's under the square root delta, or I guess this is the discriminant. If the discriminant delta is equal to 0, then the solution is lambda equals 1 minus c1 over 2 plus and minus 0. So we have only one value of lambda, but for a second order differential equation, we know we need to have two unique independent solutions. So this is the case of a repeated root. So we have to find the other linearly independent solution. So when lambda is equal to 0, then lambda has repeated roots. So we must seek the second linearly independent solution to find the general solution to this second order ODE. And now the third case is when delta is less than 0. And if the discriminant is less than 0, then we have to take the square root of a negative number, and therefore lambda has distinct imaginary roots. So in that case, we will have our two linearly independent solutions, but the solutions will be imaginary. They'll be periodic functions of cosines and sines. And so this brings us to theorem 3.6.1, which pertains to the second order Cauchy-Euler equation. And that equation states, again, for the second order Cauchy-Euler equation, where we have x squared plus y double prime plus c1xy prime plus c2y is equal to 0, then y of x, the general solution, is a, some constant, times the absolute value of x raised to the lambda 1 power plus b times x raised to absolute value of x raised to the lambda 2 power. And that's the case in which we had all real roots, and they were distinct, lambda 1 and lambda 2, and that was when the discriminant was greater than 0. Now the second case was when delta, the discriminant, is equal to 0, and in that case we had a repeated root, and that repeated root gives the solution x raised to the lambda power, which remember was repeated, and so we had to seek a second distinct solution, linearly independent solution, and it turned out that that second solution was some constant times the log of the absolute value of x. And finally, the last case is the case in which delta is less than 0. That is, the discriminant is less than 0, and that gives a complex root. And the complex root is associated with periodic oscillations. And I'll give the solution first and explain what the variables are. So y is first proportional to x raised to some power alpha, and then that's multiplied by cosine, a cosine term. So that's a cosine of another term beta times the natural log of x, and then the other part of the periodic solution is the sine function, and that's also the sine of beta times the natural log of x. So for the constants, so a and b are the integration constants, and those are the constants that you would solve for when solving for a particular solution. And let's define alpha and beta next. So remember, lambda was equal to 1 minus c1 over 2 plus and minus, and in the case in which delta was negative, we had I, the square root of negative 1, times the square root of delta over 2. And so alpha is simply the first term, that's 1 minus c over 2, and beta is the square root of delta over 2. So these are general solutions. One, when the discriminant is greater than 0, we get a real exponential sum of exponentials of x when delta is equal to 0, and then finally when delta is less than 0, that's when we get our periodic behavior. So let's look at a couple of examples. So the first example is the case in which the discriminant is greater than 0. So we have, again, our Cauchy-Euler equation of the form x squared y double prime, and our constant here is minus 2 times x y prime, and our second constant c2 is minus 10 times y is equal to 0. And so we're going to assume y is proportional to x to the lambda, and we'll get the characteristic equation of lambda times lambda minus 1 minus 2 lambda, right, minus 10 all times x to the lambda is equal to 0. And we have our characteristic equation here, which, using the quadratic formula, gives lambda is equal to minus 2 and positive 5. And so this tells us that y is equal to a times, that's our first integration constant, times x to the minus 2. That's our first value for lambda. Again, we've assumed that y is proportional to x raised to the lambda power. And our second solution is b, x to the positive 5. So this is our general solution. Now let's look at the case where delta is equal to 0. Again, just to be clear with what delta was, I want you to make sure you understand that delta is part of the solution for lambda for our characteristic equation. Where delta was equal to 1 minus c1 squared minus 4c2, where again these constants are, this would be c1 in the former case, and this would be c2 in the former case. Okay, so let's look at another example here. So here we have x squared y double prime. Our first constant is now positive 7. This is c1, and that's x y prime. And our second constant is positive 9. And again, assuming y is proportional to x raised to the lambda power, when we substitute this into this equation, we get the characteristic equation that lambda squared plus 6 lambda plus 9 is equal to 0. And so that gives lambda is equal to minus 6 plus and minus the square root of 36 minus 4 times 9 is 36 all over 2. And indeed, delta is equal to 0, so lambda is equal to minus 3. And so this is a repeated root. So in this case, to get our two linearly independent solutions, we have a constant, and then a constant times the log of the absolute value of x. So the general solution here is y of x is equal to a plus b times the log of the absolute value of x times the absolute value of x raised to the minus 3 power. And now the final case is when delta, the discriminant, was less than 0, and that gave, since we have a negative number in the discriminant, then we know we have a periodic solution. So that occurs, for example, when we have x squared times y double prime, and our first constant is minus 2 x y prime, that's c1, and our second constant c2 is positive 4. And the characteristic equation, so again, we assume that y is proportional to x to the lambda. When we substitute that into here, we get lambda times lambda minus 1 minus 2 lambda plus 4 times x to the lambda is equal to 0. And our characteristic equation becomes lambda squared minus 3 lambda plus 4 is equal to 0. And using the quadratic formula, we get 3 plus and minus the square root of b squared, which is 9, minus 16 all over 2, and that's equal to 3 halves. Plus and minus, we have 9 minus 16, which is minus 7. So we have plus and minus I times the square root of positive 7. We've factored out a square root of minus 1 in this form. Oh, and that's also divided by 2. So going back to our solution in the case in which delta was less than 0, we had x raised to the alpha power plus our two periodic functions, because again we have a complex root. So here 3 halves is alpha, and square root of 7 over 2 is beta. So our solution is equal to the absolute value of x raised to the 3/2 power times a cosine of the square root of 7 over 2 times the log of the absolute value of x plus b times sine of the square root of 7 over 2 times the absolute value of x. And there we have it. So that concludes this lecture on the second order case with non-constant coefficients. Here we looked at the specific Cauchy-Euler form of the equation. And we looked at cases in which the roots were real, in which the roots were repeated, and then the imaginary roots.